I'm very pleased to welcome our speaker today, Professor Seth Bullock, who's a professor of computer science at the University of Bristol. His very wide-ranging research interests and has started multiple different programs of study at different universities related to complex systems and system sciences. And currently, he's the director of the UKRI National Research Hub in AI and collective intelligence at the University of Bristol. We're very much looking forward to hearing what he has to say today. Please.
Thank you, Hayley. Stand over here and try to ignore the little echo of my voice. So if you're around after this and you're interested in collective intelligence and AI, I'd be very happy to talk to you about this hub that we've been running for the last couple of years. Is this going to work? But today, I want to talk to you about space, spatial embedding, in particular networks that are embedded in space. So, convenient if that little strip had disappeared on the side. So this is me. This is like a word cloud of words from abstracts of my papers. I wish that was fixable, but as far as I can see, everything is muted on my laptop. Anyway, as you can see, I work on evolutionary simulation models.
Hacking his presentation.
And you get this fine now? Because I don't hear that echo anymore.
Awesome. So I think it's like a kind of fixed property of modernity that we have a little bit of audio-visual stress at the start of anything. So yeah, I work on evolutionary simulation model. Those are the things that come out of this word cloud. Most networks is in there, but mostly I'm part of a community that might be called artificial life. So a sister community to artificial intelligence that's interested in understanding living systems by building things, building simulations, building robots, things like that. But often understanding those systems requires taking a sort of networks perspective. So networks show up in a lot of the things that I've been working on. Here's one of the things that I've been working on. The photograph is not great, but can anyone see what that is? Anyone want to take a guess? Worms? No, but it's definitely like where worms live. So this is some soil. This is a photograph that's taken straight down into a hole in the ground. Can anyone guess what is in the hole? It's a word that you don't normally say at work.
Maggots.
No, it's a hole full of poo. So this was a hole that was made by a creature as a collective latrine, right? As a place where multiple creatures do poos. There's only 2 mammals in the UK, maybe even in Europe, that build collective latrines. Can anyone guess which, like one of those 2 species? Humans. Can anyone guess what the other is? So it's badgers. So they're kind of cool nocturnal creatures that live in the UK. They live underground and they poo in a hole in the ground that they make specifically for multiple badgers to poo in. One of the cool things about that is that the latrines tend to happen at the boundary between adjacent badger sets. So a set of badgers is like a community of badgers. They all live in the same hole and they have a territory. Now the boundary between one territory and another is where they like to dig these holes and do their poos. And biologists, badger biologists, which do exist, believe that in addition to just being like a clean thing to do, to poo in one place, that the latrines might be information centres. They might be ways for one community of badgers to communicate to the adjacent community of badgers. So I kind of thought this was sort of interesting, and I found a paper that was about badger foraging, but it didn't include this most exciting feature of badger behaviour, so I wanted to see if I could easily get communal latrines to form at badger territory boundaries. So this is a hexagonal lattice that the badgers live in. So this white circle is a badger set, that's where they live, and the territory is a big hexagon around it, that's where they forage, and the little coloured dots are food, that's what they forage for. And I re-implemented the simulation of badgers, which was designed to help explain how they establish territories, and I just added some very simple pooing behaviour. So over time, badgers increasingly feel the urge to poo. They like to poo on top of other poo, and they like to move towards poo if it's been done recently. So that kind of simulation model looks like this. So these are little badgers wandering around in the world, consuming these little coloured dots. It's actually a toroidal hexagonal lattice of hexagonal lattices, which I found very difficult to conceptualize and work out which side, where does that loop around to. After a while, I've removed all of the food, and we're just seeing the fecal deposits, which is what I had to call them in the paper to get it published. And the ones that are inside a territory are coloured blue, and the ones that are at the boundary between territories are coloured red. And after many days of foraging, so they spend a day of foraging, and then they all go home to rest at night, and in the morning they all come out again and forage, and they have a very simple strategy that they just move randomly, and either they move randomly, completely randomly, or they stay within their territory. They just know where the boundary of their territory is, but they have no memory for where they have pooed before. They have no desire to establish latrines at boundaries. They're entirely random, but over time you see latrines form immediately around the set, because after they've spent all night asleep, it's time to poo, and they form preferentially at the boundary between the spatial regions, because that's where most badger time is spent, because 2 badger communities spend time at this boundary, and 3 badger communities spend time at this triple. So you end up with these kind of distributions, even though badgers have no specific cognitive or behavioural strategy. The communal latrines form at the boundaries spontaneously without any special evolutionary adaptation. What's interesting is if you destroy the spatial structure of this network, so this is a bit hard to see, but what I've done is basically reallocated all of the nodes that are neighbouring each hexagon to be other nodes within the same territory. So each territory has the same number of locations, each location has the same degree, there just isn't any spatial correlation structure anymore. And now you see, so it's still the case that these locations along the edges of the territories are the locations that 2 communities can access. They just don't access them by going through a spatially correlated set of locations that are nicely organised. They access them by going through random connections between locations. So we see some red dots. There are still latrines that are being formed at the boundaries, but we see a lot of blue dots occurring all over the territory. So destroying that spatial structure has interfered with this self-organising ability of these badgers to create latrines at boundaries. So that's little badgers rather. They're very cute when they're young. We also can look at much more disgusting animals. Does anyone know what this is? Anyone have a guess? It's obviously not a badger. It's very different. So this is a queen termite. So in this species, queen termites are about between 50 and 100 times bigger than the regular worker termites. They can't move, so she is completely sessile, and this whole activity is just producing little baby termites. That's what she does. And the key thing that baby termites do is they build a mound around their queen. First of all, they build what's called a royal chamber surrounding her. So this is a hand-drawn diagram from a PhD thesis, maybe even a master's thesis from the late 70s by this entomologist, Brunsma. So this is a queen termite, and he's drawn the locations of the first pellets of building material that the termites placed. So they're kind of equidistant from the queen's body, and they're also sort of spread out. And he's also drawn the route that the builder termite that laid the first pellet took really circuitous serpentine route, eventually placed the building material. And eventually, these building deposits grow and join up and form a dome that covers and protects the queen. But to start with, they're placed, and building material is placed on top of the first pellets, and they form columns. But the 100th piece of building material that was placed, this is the route that the termite took. Right? It's not this kind of windy, circuitous route anymore. The termite goes straight to the location that the building material is placed at. The theories about how this happens is that there's some sort of recruitment that is happening by the building material. So a termite chews up a bit of soil, spits it out. There's some kind of pheromone in the saliva of the termite, and that pheromone diffuses away from the building site and creates this zone of attraction, and that's how termites end up being able to go directly to these building sites. So a spatially mediated kind of communication system is organising the behaviour of some presumably pretty stupid little termites. And eventually, this, although it starts off very simple, these processes end up building, in some species, amazingly complicated structures. So this is a species of termite that actually farms some kind of fungus inside its nest by maintaining levels of moisture and heat that are suitable for farming fungus by designing all of these vents in order to regulate the kind of homeostatic properties of the whole nest. And we can look at modelling different strategies that the termites might use, different ways that they use pheromone, to see if we can reproduce the building behaviour, the kind of the sort of systematic, stereotypical building behaviour of the observed termites. So in this simulation, termites lay a pheromone trail back towards the queen after depositing the building material. So the building material gives off this salivary pheromone, but also they use these trails. And what that enables is this kind of stereotypical column building behaviour. We also see something that Bruinsma noticed, which he called lamellae, which is that the termites build out. They build up and then they build out, and they join those together from archways. And he also did this amazing experiment where he took each of the builder termites in a colony and varnished their abdomen. So that's where they lay trail pheromone. So that prevents them from laying trail pheromone. And when he allowed them to try to build a termite mound, they failed. They just built some low mounds. So the evidence was that trail pheromone is somehow implicated in this system. So this is a second system in which, if you interfere with the spatial communication or the spatial structure or the spatial organisation of the system, you destroy its ability to do this kind of complex organisation. And in lots of the other projects that I've been involved in, there's a similar sort of story. So this is a simulation of chemical processes within this like a vertical plane of fluid, and these are chemical species that interact together and give off heat. This is a model of a kind of American city grid, and these are vehicles that are trying to get through this grid and communicating to each other in order to avoid congestion. This is a system of robot sheepdogs that are trying to usher these little white robots into this safe zone and are interacting with a person. This little cursor is moving the sheepdogs around in an effort to try to help each other to do this job. And again, and similarly, this is a top-down view of maybe a warehouse where robots are trying to explore the whole space really quickly to see if anyone has... I think the scenario is there's been some chemical outbreak and we need to check that there's nobody left in the building. So those are all slightly whimsical, right? Badgers and termites and sort of science fiction stories about robots. But even in some of the more serious projects that I've been involved in, spatial organisation turns out to be a key property that helps you understand the system. So this is a demography project that was interested in understanding what the pressure on the UK's social care system was going to be in the future. Involved building these kind of synthetic simulated populations to try to understand whereabouts in the country and how mobility in the country was going to influence things like the amount of unmet social care need as the population ages. This, around the same time, was a project about trying to understand the interaction between different infrastructure networks in the UK, the road network, the power network, during some sort of crisis, like a terrorist attack or a flood or a whiteout. And again, the models, whether they were really abstract or whether they were really realistic, the way that those networks were organised in space turned out to be really crucial to how emergency services were going to need to respond, for example. So the story that I'm trying to draw out of all of these examples is that space matters. These are two studies that weren't by me, but were really influential on my thinking. So this one at the top here is a two-dimensional petri dish filled with different species of chemical that catalyze reactions. So the blue chemical catalyzes the reaction of the green chemical, which catalyzes the reaction of the yellow chemical. And you get these autocatalytic spirals that spontaneously arise in those kind of systems of interacting chemical species. And in this simulation, you introduce this black species, which doesn't catalyze anything else. It is catalyzed by some of the colored species, so it is created by them, but it doesn't contribute to this kind of autocatalysis cycle. It's a parasite. It leaches energy. And if you simulate this system as a set of partial differential equations with no spatial realization, so just the quantity of each of these chemicals, then the parasitic black chemical will drive the system extinct because it's effectively leaching energy out of it. But if you organize those species in space, if you just dump them on a two-dimensional space, then the spirals that they organize into drive these black species together and eventually regulate their number, keep them under control, and the whole system will survive. Similarly, on this side, we have a kind of game theory type model due to Ezequiel Di Paolo. So you have a whole bunch of agents, they're playing some sort of cooperative game, which can be exploited by parasites, exploited by defectors. And again, if you run that game in a bag of agents that all interact with each other indiscriminately, then the defectors will drive cooperation extinct. But if you spread these agents out in a continuous space, they organize themselves into clusters, they drive the defectors to the outside of the clusters, and inside this cooperation can persist and survive, even though the parameters are exactly the same, the rules of the game are exactly the same, essentially the dynamics of the game are exactly the same. Just space is what is enabling this cooperative behavior to persist. So in all of these examples, non-spatial models do not allow whatever we're interested in, the interesting behavior, to persist. The hypercycles and the cooperation fail if we don't have spatial embedding. With spatial embedding, they persist. So space is scaffolding functional complexity. It's imposing some sort of constraints which, across all of these different systems, enable some more interesting behavior to arise and persist. So if we think about that from a network perspective, what kind of networks might be characteristic of those kind of spatial systems? Well, we can look to some work by people that I know some of you are familiar with. So these are three theoretical neuroscientists from the States. And they were interested in a question that lots of people, I think, have been interested in, which is what is it about the structure of the brain that enables it to be able to support such complex behavior? And they were interested in distinguishing simple systems from complex systems. So we're pretty familiar with a diagram that looks like this. Brains are complex, they're up there, and we can think about complexity as somehow in between ordered systems, which are simple, like a lattice, and random systems, which are simple, like just a random mess. Right? And something in the middle that's not completely ordered and is not completely random, that's where the brain is. But they replace this picture with something more interesting. So on this side, we have fully integrated systems, systems in which every part is directly connected to every other part. And all those systems can do, they claim, is really sum things, right? All of the inputs get merged together and you get an averaging sort of behavior. On the right-hand side, a fully segregated system is the opposite. Every component in the system is operating independently. And again, you can't get complex sorts of behaviour out of that. And in the middle, rather than this mixture of random and order, they were interested in systems that have a balance between integration and segregation. So they're integrated, that allows all of the stuff that they're doing to be drawn together into coherent behaviour, but they're segregated. Different parts of the system can be handling different parts of the cognition, different parts of the calculation, different parts of the problem, and then they can be combined in interesting ways. So their argument is that the brain lives in this region with these kind of more interesting networks. And some work that I did with people who can do much more maths than me asked the question, what are the network motifs that contribute to that measure of TSE complexity, this balance between integration and segregation? And these are the motifs that fall out of that analysis. So if you look for small 2 or 3 node motifs in directed networks, these are the ones that contribute to complexity by the lights of this particular complexity measure, and all of these ones are the 3 node motifs that don't. And looking at those, you might already, given that I've banged on about space a lot, you might already be guessing that I'm going to point out that those nodes, those motifs come for free in spatial networks, right? Triangles, reflexive connections of every kind. And we know that in addition to space mattering in all of these kind of examples and theoretical models, we know that a lot of the networks that we're interested in are spatially embedded, right? Social networks, sexual networks, animal social networks. And we know that these networks that we're interested in have a set of characteristics, clustering, maybe small worlds, spatial constraints in that connections tend to be easier if nodes are near to each other in space, broad degree distributions, positive assortativity in these sorts of networks, and community structure. And this is the one that I'm going to be most interested in today. There's a bunch of other things as well that don't tend to crop up as often. Nodes are heterogeneous, maybe the networks are weighted. Networks tend to be dynamic in 2 respects. The properties of the nodes evolve and the net structure evolves, and those two things are co-evolve with one another, but they're reflexive. So here's a simple study to kind of play out what I think is an example of paying attention to space. It's interested in this issue of social fragmentation. It's extremely simple. Probably network science people are going to find this slightly cartoon-like, right? But we're interested in questions about how fragmentation and polarization arise. Is it always the case that it arrives deliberately? There are bad actors that are engineering that, or people are naturally predisposed towards wanting to be in polar opposite groups? Or can it self-organize inadvertently where none of the agents actually want that to happen, but it happens anyway? And the second issue, well, so we're going to be interested in 2 issues. One is what role the homogeneity or heterogeneity of the nodes might have in that. So I come from a community, swarm intelligence, collective behavior, where it's very natural to build models where all of the agents are effectively interchangeable. They're all just little nodes, and they move around in swarm, and they don't differ from each other in any interesting ways. But actually, most of the systems that we care about are not like that. We're increasingly interested in diversity, and even engineers who are building these kind of swarm systems might be more interested in making a kind of squad of agents that each have different properties rather than a swarm of agents that are all interchangeable. So if we differ in our strategy for updating our opinions, does that make a difference that we can measure? The second issue that I'm interested in is space. So it's increasingly interesting to understand the way that space constrains social behavior. So we now live in a world where we don't have to live in the same street in order to be in touch with one another, and that enables new ways of working. All of my students that graduate in computer science, I've learned not to talk to them for too long on graduation day, because they start telling me about how amazing their job is, and they're going to go and live in Amsterdam and earn money from some other part of the world. Contrasts quite strongly with the kind of family business model, local kind of constraints, keeping people in local areas becoming known for what they do because of kind of positive feedback effects, and also the constrained nature of information flow traditionally, where people had to actually physically meet and talk to each other in order for information to move around. So if social interactions are being freed from those spatial constraints, how does that impact social networks? So here are I'm going to talk about various kinds of opinion dynamics models on different networks, and here are the ones that I'm going to use to capture notions of space. So this is just a regular ring lattice. Nice because it has strong clustering, long path lengths, but no community structure at all. Every node has the same degree. Contrast, this is a random geometric graph. Scatter the nodes in a plane, connect every pair of nodes that are separated by a distance that is less than some threshold. Again, strong clustering, again, long path lengths, very weak community structure. There is a little bit of community structure because some nodes are lucky and get plonked down next to a lot of other nodes, and some nodes are unlucky and get plonked down and there isn't many nodes near them. But you can't control that community structure. It just is a consequence of the kind of Poisson randomness of the location of the nodes. And the third type of graph is this very simplistic kind of contrived network, which you divide the nodes into small groups, you construct a clique for each of those groups, and then you connect each clique to the clique next door. It's supposed to represent caves in a caveman world where the people living in a cave all knew each other, but they didn't really know many of the other caves. So what's nice about this is we still have the strong clustering, we still have the long path lengths, but now we have very strong community structure because we've effectively hand designed 20 communities that are going to be 20 cliques. So the model I'm going to run on top of this is a opinion dynamics model due to Hiroki Sayama, who some of you might know because he basically live tweets every single conference in the world. I mean, hopefully you also know him because you've bumped into him because he's really lovely. So he introduced this very simple model of opinion dynamics on an adaptive social network. I'm going to explain it very, very quickly. So every node has an opinion x, which is just a scalar number, and this x for node I changes over time as a result of conformity, which is this bit. So this angle bracket x is the average opinion in node I's social neighborhood, so sort of weighted opinion around node I. And the difference between that average opinion and the agent's own opinion drives this change parameterized by this parameter c, plus some random noise, quite small, it fluctuates every time step. So that's the only thing that's happening to opinions, is people are gradually conforming to the opinions around them. But there are other things going on to the network. So every weight between I and j, it's a directed, weighted graph, is influenced by these two processes. One process is homophily, which is a function of the pair of opinions. The other process is attention to novelty, which is a function of the average opinion around me and the opinion of this person that I'm thinking of being connected to. So if this is big, this difference, then that's a lot of novelty. This potential neighbour of mine is very different from the opinion around me. If this distance is small, if this difference is small, there's not a lot of novelty there. This person is just like the average of the opinion around me. If this distance is big, there's not much homophily. This person's not like me in their opinion. If this distance is small, there's a lot of homophily. This person is like me. So it's just the difference between these two values compared to some threshold. That's homophily. And the difference between these values compared to some threshold, that's attention to novelty. And this is the local social norm that I've described as the weighted opinion around each node. And it shows up in a few places. And importantly, there are a few parameters. So C is how strong is conformity as an influence. H, how strong is homophily. A, how strong is attention to novelty. Theta H, what's the level of homophily at which I'm indifferent about getting stronger or weaker connection to this node. And theta A, what's the level of novelty that an agent presents around which I'm indifferent about getting stronger or weaker to them. So this model, what's interesting is depending on those parameters, you can get quite different outcomes. So under some conditions, you get the network fragmenting and lots of polarized opinions. Under other conditions, the whole network collapses into one community and they share a very similar opinion. And in between, you can get interesting outcomes where there are a small number of communities that are either quite similar in their opinions or can have quite different opinions. So when you've run the model for a long time, you can use some community detection algorithm to find the communities, the number of communities, and how nicely those communities separate the network. And then you can measure this thing, community mean opinion range. Let's say you found 5 communities, you calculate the average opinion in each, and then you take what's the biggest difference. And that's a measure of kind of how polarized your network is, how much extremism is in there, is in your network. So the first thing that I was interested in doing is, instead of these C, A, H parameters being true for every node, what if every node has their own value for these parameters? So some nodes are more conformist than others, some nodes suffer or are vulnerable to homophily to a greater or lesser extent. And then using some very simple models to try to work out what influence that has on the communities and whereabouts different nodes end up. Right? If you're a high conformist, will you end up in the middle of a community? Will you end up in one of the average opinion communities? If you have very low homophily, does that mean you're going to end up between communities? So the main result that I was interested in, so this is comparing a network with heterogeneous nodes, where every node's values were drawn from a distribution, compared to a homogeneous network where every node has the same strategy, the same parameter values, and they're the average of these guys. So mean field, these are the same system, but because of the compound effects of these kind of non-linear interactions in this update function, they end up behaving very differently. So here you can see, I mean, this is obviously a bit hard to tell, apart from the fact that that looks different to that. I hope you would agree. But here you can start to see this nice graded sort of distribution of nodes. Nodes with this, they're coloured by opinion. So nodes with this kind of cold opinion end up over here, not very well connected to nodes with these hot opinions. Whereas here, the layout algorithm is struggling to find a way to lay out the nodes in a nice structure. And if we look at that a bit more carefully, we can see a couple of things here. First thing is, there are stronger colours in this side. There are more extreme reds and more extreme blues. So the heterogeneous network generates nodes with more extreme opinions than on the right-hand side. And here you can see a much more segregated set of communities. There's a triangle community up here that's connected to this circle community, that's connected to this square community. But the layout algorithm finds it easy to put the triangles up here and the squares down there, because the triangles don't connect with the squares so much. The layout algorithm is really struggling here, because all of these communities are interconnected. You can start to look at things like, where are different strategies? So like I just said, this one is more integrated, this one is more segregated, this one has more extreme agents in it, this one has more moderate agents in it. But also you can find things like agents with abnormally high attention to novelty are right here in the middle, basically connecting the communities together, because they're interested in, as soon as they join a community and that community starts to conform, they get interested in a different community. So the results from this model, just adding heterogeneity, not changing the average properties of this network at all, drives extremism, but inhibits fragmentation. So previous models, I think, when you get extremism, it tends to be because the network has fissioned into different communities that are effectively independent from each other and therefore can settle on different opinions. But here, we end up with a network that is still fully connected and where the communities are actually fairly well connected to each other, but the communities maintain diverse opinions, because the attention to novelty glues the agents together, and the nonlinearities in the update function create this kind of positive feedback that drives nodes into more extreme opinion states. So no space in that, like, I'll contrast with every single other thing that I've been talking about, but pretty easy to add space. So, you know, instead of a bag of nodes where they're all equally likely to be connected to each other and interact with each other, we could distribute the nodes on a lattice. That's maybe a standard sort of option, but I'm interested in understanding the different things that space brings to the table. And then one way of understanding that is to create spatial networks and then erode the spatial structure and see how the things that we care about change as we erode that spatial structure. So this diagram from Watson-Strogatz, for like on their small world paper, we start with this, which is the most spatially constrained network, and then we gradually rewire some of the edges until eventually we have a completely randomly structureless network. The first thing that I had to worry about, and I can't, like maybe other people have worried about this, is how to do that random rewiring in a way that doesn't mess about with some of the things that that it does mess about with the thing that we want to erode and doesn't change other things. So a default rewiring scheme, a sort of standard naive rewiring scheme, would be, okay, there's a chance that we want to rewire an edge. So here are two edges that we have chosen randomly to rewire. We find two more nodes and we take away these edges and we add them to the random nodes, right? So we're removing the spatially constrained edges and we're adding random non-spatially constrained edges. If we do this completely, we will end up with a completely structureless random graph, but we're changing some other things at the same time. So this node ends up having the same degree after it was rewired, but this node has lost a neighbor, and so was this one. And these two nodes have gained a neighbor. So we're changing the degree distribution at the same time as we're getting rid of the spatial structure, which we might not want to do, because I want to be able to say that the things that have changed in the dynamics of the opinion dynamics model were due to the loss of spatial correlation, not due to moving towards a particular degree distribution. So a naive alternative to that would be, well, okay, we've got these two edges and we want to randomly rewire them. We could remove them and add edges to the other nodes that are losing a neighbor. So here, all of the nodes end up with the same degree distribution, but because the edges that we're removing are necessarily short, they're spatially constrained, and the pair of nodes that we are considering is arbitrarily distant, probably half the space away. We're going to end up adding these correlated highways between different parts of the network. So that's not ideal, but we're introducing a kind of a correlation where we actually want it to be just kind of gradually removing the existing spatial correlation. So a more smart rewiring scheme is to decide on all of the edges that we're going to rewire. So go through all of the edges, toss a coin, are we going to rewire that edge? And then randomly assign new edges between random pairs of those nodes. So those are guaranteed to be in random parts of the network. We'll end up with the same degree distribution as before, no spatial structure, and we haven't introduced any spurious correlations or distorted the degree distribution. So what happens? So if we start with a lattice and we randomly rewire it in this smart way, then we get this very, very mild effect on this community mean opinion range, the amount of extremism, the degree of polarization, the amount of diversity of opinion in the network. Possibly there's a little bit of a kind of small world effect, but I don't think it's really there. If we look at the random geometric graph, we get even less of a signal. We do get a lot more variation because I think the initial conditions of a random geometric graph are random and the degree of community structure that was there is varies from random geometric graph to random geometric graph. And it turns out that it is the community structure eroding that is what is responsible for getting rid of the extremism. So the spatial connected caveman graphs, before you start eroding them, they have significant amount of this community mean opinion range. But as you start eroding them, you lose that very quickly. And if we change our connected caveman graph so that the caves are more connected to the adjacent caves, right? We could just connect them with one edge. That's the minimum amount of connectivity around the clock, but we could connect them with 2 or 5. And as we do that, this effect goes away because we weren't starting with very much community structure in the first place. So what's going on here is the spatial community structure was supporting this kind of multiple consensus opinions. Different communities were able to maintain different opinions. And so space was sort of passively enabling polarization. It wasn't really encouraging it. Random rewiring was destroying that because it was destroying the community structure, not because it was destroying the clustering coefficient, not because it was introducing long distance paths, because they didn't look like there was a small world effect. It was definitely the community structure that was the only thing, pretty much. I mean, there was this very weak effect in the first graph, so possibly clustering is having a small effect. One thing that is maybe worth exploring here at the moment, you know, one of the things, I mean, one of the ways that I set this up is that in the modern world, we're not constrained to only be friends with people who live next door to us. We could be friends with people on the other side of the world. And this kind of eroding of spatial constraints was a kind of attempt to capture that. But when I become friends with someone on the other side of the world, it's not a random person. It's somebody who I share something with, some reason for me to be friends with them. So far, we've just been rewiring in an indiscriminate fashion. But it would be interesting to look at whether something more opinion-driven would maintain this kind of extremism. Right? So we could sacrifice spatial structure and still maintain opinion alignment between adjacent nodes. Is that enough? Is that possible? How hard is it? It's actually not been easy to think about how to make that work. And the other thing that isn't happening in this, which is happening in online social networks, all of my nodes are just following the laws of society, right? They conform to the people around them, they get connected to the people they're interested in, they get connected to the people that they share an opinion with. No one is strategically trying to win connections. If you add those people to this model, does it change things? Can that drive extremism? So that's something that I've been looking at with these two students. So I'm conscious that we started quite late, so I could skip to the end now, or I could just tell you a little bit about a particular kind of spatial network that I think might be interesting. I'll do that for I'll see if I can do that really quickly. So this is also going to feature some people that some people in the room know. So the last model I think is kind of interesting, but I think the main takeaway question, the main sort of takeaway for me is it was a bit frustrating to use lattices, random geometric graphs, connected caveman graphs. None of them really were that useful. None of them really captured all of the properties that I cared about. Remember when I showed you the slide with the sexual contact network and the killer whale network, and I had all of these kind of properties that are my wish list, right? So the work that I did with Alberto and Marco and others was an attempt to create a random spatial network, a class of random spatial networks that had all the things that I was interested in. So here they are, right? I want these things. I want to be able to control the clustering, path length. I want it to be spatially constrained. I want there to be a broad degree distribution, or at least the possibility of it. I want there to be some positive assortativity. I want there to be some community structure. And ideally, I want to be able to independently control those things so that I can run processes on that network and see which of these things is driving contagion, which of these things is driving fragmentation. So this is the model that we came up with. It was based on something that Alberto and Marco had already done, which was basically a random geometric graph where each node was connected to the nodes that were nearby to the extent that it could afford those connections. And connections cost an amount of energy proportional to the length. So it's like a kind of sparsified RGG. Maybe there's 10 nodes within reach, but I can only afford to be connected to 5 a random sample of them. And then if you give the agents more or less energy, they can be more or less connected, but they're spatially constrained. So I thought that was a good starting point, but what I wanted was some way of creating community structure. There still isn't any significant community structure in that because it's just like a sparsified random geometric graph. So here, the regs model, all the capital letters stand for something. So R is for reach, the distance that constrains who you can be connected to. R is the extent of your social reach. The distance between two nodes, I and J, that are connected must be less than R. E is for energy. Each node has a finite quantity of energy, and that gets spent on maintaining its connections to its friends. D, the cost of an edge is proportionate to the distance between the two nodes that it connects, just linearly proportionate. And S stands for synergy. The cost of an edge between I and J varies inversely with the number of network neighbors that we share. So if I want to maintain a relationship with Alberto, it helps if we both have friends in common. That lowers the cost of maintaining that edge. So that means you end up with this sort of situation where B can't be connected to D, it's too far away. B can be connected to C, and B can be connected to A, and it's actually cheaper for B to be connected to A and C because they're friends. And this is the formalism for capturing that proportionality. So the cost varies linearly with the distance, and it is scaled by this synergy value, S. S can vary between 0 and 1, it's just a big parameter. If S is 0, then the cost is just the distance. If S is 1, then the cost is 1 plus the degree. Sorry, the cost is the distance divided by 1 plus the shared number of neighbors. Oops, so this is just going to be the same slide all over again. Yeah, so it collapses to this when S is 0, and it collapses to that when S is 1. What does it look like? So I think I've already explained this. Distribute n nodes uniformly in the unit square, just like you were making an RGG. Pick a node I, pick a node J that is within reach, connect them if I and J can afford the connection. And then keep going. Pick another random node and try to pick another random potential neighbor and try and connect those, and stop when none of the nodes can afford any more edges. This is a bit of an issue. As you add the edges, the energy budget of the nodes can go up and down, right? Because if two of the people I'm connected to become friends, suddenly they're cheaper, and I've got some free energy. I might not have had enough energy for any more edges, and now I do. So we're going to come back to that at the end. What is this idea of synergy? This is the way that I think about it. Here's me at work wearing the tie. I want to maintain a relationship. I want to have a connection to this other person. We have to meet and talk to each other. I have to invest time and energy in getting to the same place as them and spending time talking to them. And if I want to maintain a relationship with someone else, then that's extra energy. But if we all work together, I can kind of get double duty, right? I can maintain a relationship with all three of these people at the same time because we all are friends with each other, or we're all connected by the fact that we work in the same place. And if I meet with this person and we talk about someone else who we share in common, that's a cheap way for me to kind of partly maintain my relationship with them, right? I learn who they're going out with, or I learn what they're doing these days for a hobby, or potentially we share the cost of buying a present for them, right? So these kind of the synergy that comes with kind of shared support, shared social support, reduces the cost to the extent that we're part of some sort of community. So that's what synergy means, and I think it maps onto lots and lots of different things, like social things of various kinds, and possibly biological things, and maybe even physical things. Here's what these networks look like. This is a REDS network with zero synergy, so it's just a kind of sparsified RGG. So the dark red nodes have higher degree, the dark red edges have higher cost. And in all these examples, we've got 1,000 nodes and the social reach is 0.1. So here, when S is 0 and the energy is 0.15, you just have a sparse random geometric graph. It has a certain mean degree, a certain amount of clustering, a certain amount of assortativity. If we ramp up the synergy to 1 but keep the energy the same, you can see these pockets of community structure that form spontaneously. We get a denser graph, mean degree 12, much stronger clustering, much stronger assortativity, and strong community structure. Dense communities separated by a kind of hinterland of sparsely connected nodes. But that's an unfair comparison, right? Because this graph has loads more edges. So of course it can have more kind of structure in it, it can have more stuff in it. So we can compare it to a kind of null control condition where we put the S back to 0, no synergy, but we ramp up the energy so that we get the same average degree. So this has the same number of edges as the previous graph, but it doesn't have the same clustering. It has weaker clustering, weaker assortativity, and less community structure because those edges have not been organized by this synergy effect. So when we look at the space of E versus S, so this is S increasing synergy, this is E increasing energy, then up here there's a kind of boring saturated RGG regime where they have enough energy to connect with everybody that they could possibly connect with. And outside that, there is this sparse regime that is much more interesting, especially when we get to the kind of like near this boundary. So in particular, over here, the assortativity kind of ramps up in that area where synergy is high enough that the energy ends up creating this kind of positive feedback, and we end up getting communities. A saturated RGG-like region and a more interesting sparse regime. So what we've got here is a new class of network that has everything that I want. We haven't shown short path lengths yet because I haven't started randomly rewiring it like you would randomly rewire a lattice. But we can start to think about looking at fragmentation or contagion on these kind of networks and see how they differ from standard ones. This is just 2 slides about what contagion looks like. So we just use a very straightforward SIS model. And what this graph is showing is as we randomly rewire networks, either the REDS network with maximum synergy or a standard RGG, this is the critical infectivity value that enables an epidemic to work. So on an RGG, your disease has to have a infectivity parameter. The probability that you get infected by contact with someone with the disease has to be up here. But on the equivalent REDS model, it can be much lower. They support epidemic outbreaks much more readily. And as we get to the kind of small world regime, potentially it picks up. So we can look at a slightly more nuanced picture of that. So there's no data on this yet, it's just empty, so I can explain it to you. This is going to be a heat map where up here we look at different infectivity rates for our outbreak, and along here how much rewiring we have done, and we're going to colour each cell by how big the final outbreak was. So we get a graph that looks like this. No outbreaks work when the infectivity is too low for random geometric graphs, but above this critical value we start to see outbreaks. And then once we're up here, once we've completely rewired into a random graph, then we're seeing quite big outbreaks. But when we move to the REDS networks, same size and same number of edges, then we see outbreaks for much less virulent diseases, and the size of the outbreaks gets very big. And we see a small world effect here, where when we're rewiring in this kind of small world regime, the outbreaks start to get big for less infectious outbreaks. So this kind of thing can make a difference. We could look at these sorts of models as a substrate on which to explore the kind of processes that we're interested in. And in the future, we could look at a whole bunch of things. For example, what if the energy that a node had resulted from it playing games with its neighbours, winning game theory games, and then some nodes have more energy to maintain networks and some nodes have less? What if nodes move around in space? What if we have a much more full model of gaining and losing edges as you accumulate energy and lose energy? At the time, I was very interested in interdependent infrastructure networks. So we could look at much better models of cascading failure on layered networks of road and power if we had models like this. But this is the key problem. Well, maybe two. The first is they're really expensive to build. This process of adding edges and checking all the costs and seeing whether a node can afford a new edge is really slow because the cost of all the edges is changeable. When you add an edge, it changes the cost of some of the other edges, so that really slows things down. And possibly because of this, there wasn't much interest in them when Alberto and I published the papers. So is there an alternative, right? Is there something that can fill this niche, which is fast and easy, you could scale to networks bigger than 1,000 nodes, but allows us to look at these properties of community structure, clustering, path lengths? Okay, final slide. So, right back at the start, I told you space matters. It does make a difference, right? Abstracting it away changes the outcomes of processes, models, games. It's crucial to enabling the kinds of behaviour that we're interested in. So we have to find a way to include it in I think, a sophisticated and tunable way. And the thing that I've been doing, you can probably tell I'm more of a toy simulation person than a maths and physics person. So what I do is I build little simulations and run a lot of them and collect them and look at graphs, and then I try to find physicists who will do the analysis for me. The problem is finding physicists who will do the analysis for me and I can understand what they've done. Some kind of simple class of random models, like a Barabasi-Albert model or an Eder-Schrödinger model. So I need like two people with complicated to pronounce names to formulate a new model that has spatial embedding as a kind of first-class citizen model and is capable of controlling the degree of community structure. That would be super useful. Maybe there's something out there already, right? I'm not really very well embedded in the network science community. Maybe this already exists. Or smart people could develop something that would be super useful for looking at this sorts of questions. Thank you very much. Sorry, that took a bit long. Let's take questions. The first thing is there a class of spatial models that you think I should be using?
I don't know about spatial models, but as you were sort of talking about the constraints that you want the network to have, I was thinking of stochastic block models. I'm not sure if that's something that you're familiar with. Just like a suggestion that, because we've used them in neuroscience, which is a spatially constrained network, it's spatially embedded. It's been a decent null model so far.
So do you have to pre-specify how many blocks you want, what their connections are going to be?
Yeah, you can vary those parameters, but it's useful for defining in priori, in general, how you want your community structure to look.
Right.
Okay. And you can inform those parameters by their spatial embedding.
Yeah, I guess thank you, that sounds fantastic. And I could look at those a bit more. I think when I did look at them, I felt like I wanted the community structure to arise organically out of the process rather than be pre-specified. But I realised that I might be a bit, that might be being overly kind of demanding, right? So there are some things that I'm willing to specify, and I want other things to just kind of emerge, and maybe I should be more flexible.
Are you familiar with the work that Martin Novak?
Yeah, well, some of it. But yeah, so are there particular things? I guess the thing that I'm thinking of is the kind of games on lattices type work.
Spatial process lemma and crystal level networks. And that's what.
Yeah, so one of the things that's interesting about that is, and I think it speaks to the sort of rigidity of the do things on lattices idea, like a lattice that maybe wraps around. So every node has the same number of neighbors, and we're going to update that lattice. So Novak and May got a science paper, I think, Christensen on a lattice, these lovely kind of Turkish carpet-like patterns of defection and cooperation, and they spread over time, and it was very kind of complicated. Two other people, Huberman and Glantz, basically re-implemented that, but with asynchronous update of the nodes. Right? So the original model, everyone plays all the games, everyone accrues the reward, everyone looks at their neighbours, spots the neighbour that has got the most reward, and decides, I want to play that strategy next time, and then everyone changes their strategy simultaneously, and we have another go. And all Huberman and Glantz did was say, well, let's just let the nodes change their strategy out of step with each other. Right? They all change their strategy one after the other, instead of everyone agreeing, okay, now it's time to change the strategy. And they have a lovely figure in there. It was published in PNAS, Papers Not Accepted Science. So it was like, I think they were quite clever to go for that journal because they were taking down a science paper. But their equivalent figure, instead of this lovely Turkish carpet with red and blue and green and yellow, showing all of these different tit for tat and whatever strategies, theirs just is red, just defection. As soon as you take away the rigidity of the sort of, we're going to treat the system as though it is clocked and controlled, then immediately the interesting pattern goes away. It was entirely an artifact of this kind of strange synchronous updating. My suspicion is that you might get something similar if you relaxed that lattice-like, I should have a look at this, but if you relax that lattice-like regularity, everyone has the same number of neighbours, then I think you possibly would get something similar. Yeah, okay. It's quite possible that they did follow-up stuff after that that was also more useful and launched.
I was thinking of the work of Francisco Santos, also his dynamical models, even if he doesn't word them as spatial embedded, but the rewiring process was already enabling a lot of cooperation that without that would be impossible, even more for the visitors dilemma and so on. So there is something to that. And to the point that Haley was making with the stochastic block model, it could be that you could overlap some generative model on top of that, so it would be halfway of what you want to do with already something that could give you a baseline. It's true that you need to tune a bunch of parameters depending on what you want to obtain from the model.
Yeah, so my feeling about the block model is, so the random geometric graph starts with all the nodes uniformly distributed across the square. And my race model also starts with all the nodes randomly distributed across the square. But there's nothing to prevent me from having a non-uniform distribution of nodes. And that would create a community structure, right? That, let's say that I create two blobs of nodes, two Gaussian distributions of nodes. So there's nodes everywhere, but there's two real focuses for them. And then you run a random geometric graph over that, and you will get what I spend hours and hours and hours running this synergy process, and you could get the same thing. But you would have to have pre-specified, I want two communities, right? There's something in the geography community called point processes, where it's a little algorithm for putting points on a plane. And I spent ages in this literature, well, I should probably go back to it with ChatGPT, but I thought it would be obvious that one of the point processes that they would want is something that generates multiple clouds of points. You place a point, the next point that you place is factored on where the previous one was. So you could go, with probability P, put the point anywhere. With probability 1 minus P, put it near to the point that you just placed. And if you got P and 1 minus P correct, you would presumably get some, a succession of little groups of nodes. So I thought, so that might be one way of doing it. It's a bit like setting up the block model. It's like I'm going to have some blocks, but the blocks are just going to be groups of nodes in the plane, and then I build the network on top of them very quickly. But I couldn't find a point process that did what I wanted. I also have experimented with sort of gravitational models. Randomly distribute the points on the plane, and then let the points kind of gravitationally attract each other for a certain amount of time. And I assumed that I would get, first of all, there would be little kind of clouds would happen, and eventually they would all collapse into like one place. But I couldn't get that to work either. They just all collapse into one place, and it's very boring. But something about placing the points would be a shortcut to a spatially embedded community structure graph. I need to have a good algorithm for organising the points in the space.
Let's thank our speaker for the wonderful talk. Typically after talks we go out for pints afterwards.
That's why I'm here.
Perfect.